Here's another tree diagram example. 2% of the adult population of a country is carrying a virus. A test is developed which finds the virus in 95% of the people who have it, but which also finds the virus in 10% of the people who don't have it. If the test returns a positive result, that is, it finds the virus, what is the probability that the person tested actually has the virus? Now, there are three conditional probabilities involved here. This one is the probability of getting a positive test result if the person has the virus. This one right here is the probability that somebody has a positive test result if they don't have the virus. The question here is about a third conditional probability. What is the probability that a person who gets a positive test result actually has the virus? So what we're looking at here is the probability of having the virus given that the test result was positive. You notice this is backwards from that. This conditional probability has the condition reversed from that one up there. This is what they call reversing the conditioning, and it's very commonly seen in probability questions like this, and tree diagrams are really useful for answering questions of this type. Now here's our tree diagram down here. Since we're given these conditional probabilities based on whether somebody has the virus or doesn't have the virus, having the virus comes first in here. So at this node right here, the question is, does somebody have the virus? And somebody might have the virus or they might not. And we know these probabilities, 2% of the population has the virus, so this probability would be 0.02. The probability that somebody does not have the virus would be 0.98. At this node, this is where the test comes into play. And somebody's either going to get a positive test result or a negative test result. They get a positive test result 95% of the time if they have the virus, so this probability would be 0.95. And they get a negative test result 5% of the time if they don't have the virus, if they do have the virus rather. If they don't have the virus, they're going to get a positive test result 10% of the time and a negative test result 90% of the time. And from this we can figure out our outcomes and the probability of each outcome and make a little chart. The outcomes you can get by going along the branches. This is having the virus and getting a positive test result. This branch is having the virus and getting a negative test result. This branch leads to not having the virus and getting a positive test result. And this branch leads to not having the virus and getting a negative test result. The probabilities we get by multiplying along the branches, and 0.02 times 0.95 is 0.019. 0.02 times 0.05 is 0.001. Notice these two probabilities add up to 0.02. 0.98 times 0.1 is 0.098, and then 0.98 times 0.9 rather is 0.882, and these two probabilities add up to 0.98, and the whole list of probabilities adds up to 1, as it should, and we're all set. Now we're ready to answer our question. This conditional probability right here, the probability that somebody has the virus given that they had a positive test result, is the probability of having the virus and getting a positive test result divided by the probability of having a positive test result. Let's find that first. The probability of getting a positive test result is the sum of these two probabilities, the probability of having the virus and getting a positive, plus the probability of not having the virus and getting a positive. And that is 0.019 plus 0.098, and that adds up to 0.117. And then the probability that somebody has the virus, given that they had a positive, is the probability of having a virus and getting a positive divided by the probability of the positive. That is 0.019 divided by 0.117, and that is approximately 0.162. So about 16% of the people who get positive test results actually have the virus, and about 84% of the people who get positive test results don't have the virus. This is something that a doctor should be able to explain to a patient. If a patient gets a positive test result, it should be reassuring to know that 84% of the people with positive test results actually don't have the virus, and that person could be retested if they get a positive. So this is something that people in the medical field need to know. It's also something that people in the legal field need to know. This comes up in trials, in criminal cases and civil cases, a lot. And it's something that people need to understand if they're going to serve on juries, etc. So it's an important issue in probability, and it shows up in a lot of real-world circumstances. Now the question is, why is this probability so small? Well, take a look at this. This is 95% of 2%. That's a very small number. This number is 10% of 98%, which is a much larger number. And since this is much larger than that, because basically the virus is very rare in the general population, this number is much larger than that, and that means that this, as a fraction of the total of those two things, is pretty small. So that's why the probability worked out the way it did.